In digital communication, errors are inevitable. Whether it's static on a radio line or a scratch on a disk, data gets corrupted. To fight this, we use channel coding, adding structured redundancies so the receiver can detect or even fix mistakes. We generally split these into two families: convolutional codes, which process data in a continuous stream, and linear block codes, which group bits into fixed size packets. How do we handle an error once we find it? We have three main strategies. Automatic Repeat Request, or ARQ, detects the error and asks the sender to try again. Forward Error Correction, or FEC, is more proactive. It includes enough extra information to fix the error on the spot without asking for a resend. Finally, Hybrid ARQ combines both, using FEC for small fixes and requesting a repeat only for the big ones. Let's look closer at linear block codes. We take a block of n information bits and add m bits of redundancy to create a code word of length k. We call this a CNK code. The code rate, R, is the ratio of information bits to the total code word length. The higher the rate, the more efficient the code, but the less room it has to correct errors. To measure how distinct these code words are, we use Hamming distance. It's simply the number of positions where two binary strings differ. For example, the distance between 1101 and 1001 is 1, because only the second bit changed. The minimum Hamming distance, or D0, of a code is the smallest distance between any two distinct code words. This single number tells us exactly how many errors the code can handle. Think of code words as points in space. If we draw a sphere around each code word with a radius t, and these spheres don't overlap, we can correct t errors. Specifically, if our minimum distance is d0, our correction power, t hat, is the integer part of d0 minus 1 divided by 2. If d0 is 5, we can reliably fix two errors. Any more, and the received word might fall into the sphere of the wrong code word. When a message arrives, how does the receiver decide what was actually sent? Maximum likelihood decoding chooses the code word that is most likely to have produced the received signal. In a symmetric channel, this is equivalent to finding the code word with the minimum Hamming distance to what we received. We pick the closest neighbor in our binary space. Mathematically, we generate these codes using a generator matrix, G. By multiplying our information vector I by G, we get our code word. In a systematic code, we arrange G so the original information bits appear directly at the start of the code word, followed by the parity bits. This makes it easy to extract the message after decoding. It's a powerful framework that keeps our global networks running, one corrected bit at a time.